Hello, pre-calculus students. Today we're going to learn about rational functions. And as you can see by the screen I'm sharing, a rational function is, we're going to take one polynomial and divide it by another polynomial, and we're going to get some really funky graphs out of that. Obviously, these are not zeros. P's, in other words, it's not the graph of y equals 0, because then you'd have no fun. So I'm going to show you a technique that I use for analyzing these rational functions. The first thing I do is I write these letters over here on the right side of my paper when I'm looking at a problem. That stands for horizontal asymptote, vertical asymptote, slant asymptote, zeros, and holes. So horizontal up here, holes down here. Let's talk about the horizontal asymptote first, if one exists. Think of a parabola. It's got no horizontal asymptote. So here's the function that we're looking at. Y equals x squared plus 7x plus 12 divided by the quantity 2x squared minus 5. When we're talking about a horizontal asymptote, we want to know what is happening as x approaches plus or minus infinity. So what's going on way out there at the positive x's? What's going on way over there at the negative x's? Now, if the numerator exponent is greater than the denominator exponent, so here's the numerator degree, here's the denominator degree. If it's greater, there's no horizontal asymptote. Think of x squared, and you think of it as y equals x squared over 1. So the bottom degree is 0, the top degree is 2, because it's 1 x to the 0 power in the denominator. And that parabola doesn't have a horizontal asymptote. If the numerator exponent is equal to the denominator exponent, which is what we have here, then what you do is you just look at the leading coefficients. So this is a 1, this is a 2. The horizontal asymptote is y equals 1/2 in this case. And the way I can tell that by looking is, if you were to multiply top and bottom by 1 over x squared, you'd have 1 plus 7 over x. Oh, you know, I'm going to do that on the next page, so we won't do that here. If the numerator exponent is less than the denominator exponent, let's say this was 2x to the 5th here, can you see that 2x to the 5th is going to grow as x gets out to infinity? That's going to be such a bigger number than x squared that this divided by this huge number will always give us y equals 0. So if the denominator degree is bigger, you get y equals 0. If the numerator degree is bigger, there is no horizontal. And if they're equal, you find the quotient of the leading coefficients. And here's how I got that number. That looks like it might be a bit intimidating. Let's cover up a bunch of this. I think I'm allergic to staying after work on a Friday to make videos. So multiply top and bottom by 1 over x squared. You can see I get 1 plus 7 over x and 12 over x squared in the numerator. And I get 2 and negative 5 over x squared in the denominator. Well, as x goes to infinity, 7 over infinity is 0. 12 over infinity squared is 0. Negative 5 over x squared, or over infinity squared, is 0. So I'm just left with 1 over 2, 1/2. F of x equals 1/2. So that means as x goes to infinity, this function is approaching the line y equals 1/2. So the way you figure this out, how do you know what to multiply by here? You're going to divide by the highest power of x that you see. Here it was x squared, so we multiplied by 1 over x squared, which is the same as dividing by x squared. Here, The highest power of x that I see is x to the fourth. Now, I already told you if the numerator power is bigger, there's no horizontal asymptote. Let's see why. Divide by x to the fourth, you get this. Divide by x to the fourth down here, both terms in the denominator go to 0. So we end up with 1 over 0, which is undefined, which means there is no horizontal asymptote for this. So here's one where the degrees are equal. Here's one where the numerator degree is higher. Here's one where the denominator degree is higher. And you can see that by dividing everything by x to the fifth, I get 0 on top and a 1 on the bottom. So that's why y equals 0 is the horizontal asymptote if the denominator is going to be bigger, because the numerator will always go to 0. Denominator power is bigger, because the numerator will always go to 0. So that's how we find a vertical asymptote. Let's go next to the horizontal or vertical asymptote. Well, here I would say I have an x squared in the numerator, because that's x times x, and I have an x in the denominator. There is no vertical because the degree of the numerator is higher. Vertical. To get a vertical asymptote, you ask, what causes us to divide by 0? If x equals 3, we'd be dividing by 0, and your graph goes off to infinity. So that means the line x equals 3 is a vertical asymptote. A slant asymptote occurs where the numerator degree is exactly 1 degree higher than the denominator degree. Well, this is an x squared, this is an x. We might have a slant. You cannot have a slant and a horizontal at the same time, because a horizontal asymptote looks like this. A slant asymptote looks like this. And your graph, if you're going out to infinity, your graph can't be approaching both of these at the same time. So you can only have one or the other. And so the way that we find a slant is we notice that the degree is 1 higher than the denominator, so we divide. This is x squared minus 3x plus 2. And I'm dividing by x minus 3. So that gives me y equals 1x plus 0 with a remainder of 2. And that 2, we can put it as 2 over x minus 3. Now, as x gets bigger and bigger and bigger, this term goes to 0. So in this case, our slant asymptote would be y equals x plus 0, or y equals x. Now let's find zeros. Well, zeros, I think we can all agree if the numerator is 0, 0 divided by something is 0. So whatever x value makes the numerator 0 will make y 0, hence we'd have zeros. So I can tell by looking, especially since this is in factored form already, that an x of 1 or an x of 2 are going to be 0. So that's where it's the only places where the graph's going to cross the x-axis. Be sure that you write the line x equals 3 and x equals 1 and 2, and y equals something if it's a horizontal, or y equals x. Don't just write 3, 1, 2. You'll see why later. And lastly, there's a hole. You may not have encountered this before. So here's our function. It's x squared minus 3x plus 2, all divided by the quantity x minus 2. You can see that for every value of x except 2, these are going to cancel. But 2, you might say, well, 2 should be a vertical asymptote. No. If you have the x minus 2 in both the numerator and the denominator, they cancel everywhere except at x equals 2. So 2 is not in the domain of this function. So everywhere except 2, this function is equivalent to the line y equals x minus 1. It's just that it's not defined at the point 2, 1. So there's a hole there at x equals 2. And you could see that if this weren't there, it would be the point 2, 1. But the hole is at x equals 2. So we've now covered all of those 5 letters on the right side of the paper. Horizontal asymptote, vertical asymptote, slant asymptote, zeros, and holes. Oh, this is so scary. I think I'm going to let you write this down, and I'll explain it in class. So go ahead and pause the video, copy this down as you see it, and then I'll work it out step by step in class. All right, now that you've copied that down and hopefully you didn't have a headache from doing so, let's take a look at a little bit easier problem. And that would be this one. Y equals x squared minus 4 over x minus 2. Top degree is 1 unit higher than the bottom one, so there is no horizontal. You might think there's a slant, but I'll show you why there's not. If you factor this numerator, you get x plus 2 times x minus 2. Oh no. There's no slant either, because these x minus 2's cancel to make a hole. So the graph is equivalent to y equals x plus 2, which is already a line, which is what a slant asymptote is. So this isn't really approaching a line, it is a line. So there's no slant. So we just graph y equals x plus 2, and then we take out the hole at x equals 2. And if x equals 2, y would equal 4. So there's my hole at 2, 4. So the hole is at x equals 2. And again, if those x minus 2's cancel, the 0 happens where x equals negative 2. And sure enough, there it is on the graph. And here's another one. Holy moly. Copy this one down. These are minus signs and plus signs. Just copy this down. We'll go over it step by step in detail in class. Okay, while you're writing this down, did you try to figure out where this y equals 2 came from? Did you try to figure out where these two vertical asymptotes came from at x equals 2 and x equals 3 based on the graph? Did you figure out where this hole came from? Did you figure out where these zeros came from? Did you figure out why there is no slant asymptote? You should be able to do those things now. How do we find a slant asymptote? Well, we have to do division. In this function, the division's pretty easy. I could take each of these terms and divide it by x squared, and that's what I'd get. But if that were x squared plus 1, for example, I'd actually have to do some polynomial long division to get this. This is not a slant asymptote. All this is out here is rewriting this. Now, what happens when x goes to infinity? Well, the 1 over x term goes to 0. The 1 over x squared term goes to 0. And what happens is you're getting closer and closer to the line y equals x plus 2. So that is our slant asymptote. And if you'd like, I'd recommend going to Desmos now while you're watching this video, typing in this function. Make sure you put parentheses around the numerator. Type in this function. Type in as a second function y equals x plus 2. And then as you zoom out, you'll see that as x gets bigger and bigger and bigger, this function gets closer and closer to this line. Amazingly enough, that's the end of this instruction. I recognize that rational functions are not the easiest thing in the world. So as I said, we will go step by step analyzing those functions, doing the horizontal, vertical, slant, zero, and whole analysis, and also the sign chart, because we're going to kind of freehand graphs without ever doing an input-output table. We're going to use only a sign chart and our knowledge of where the asymptotes and the wholes and the zeros are. So hopefully I haven't scared you off too much after that one, but as I said, for me, it's Friday afternoon. I'm calling it quits. Have a great day.